Hello everyone, welcome to the Electrochemistry packet. This is our second to last packet. Hopefully you're looking at this in the first week of May. So this one, second to last. The next one, the nuclear chemistry packet, will be our last. And the last lab assignment is actually very much mingled with the nuclear chemistry packet because it's a nuclear chemistry lab. Obviously, we can't really go to the lab and do nuclear chemistry, so it's kind of a worksheet. So, you know, we'll combine those two in the next video kind of thing. All right. So, let's start to talk about electrochemistry. Now, hopefully you remember a lot of this from Chemistry 101. Okay, it's that redox thing. Okay, so all electrochemical processes are redox processes. And to remind ourselves what that means, redox, it's kind of an acronym, and it combines two words. Red is from reduction and ox is from oxidation. So reduction, oxidation, okay, these processes occur simultaneously. So if we think about any kind of ionic process, so two atoms bump together, one goes plus, one goes minus, an electron was transferred, right? Turns out that if we think about electron movement, oxidation is lost. So if something becomes oxidized, it's lost electrons, all right? So an element or compound that loses an electron or electrons is said to be oxidized, right? Oxidation is loss of electrons. And then, you know, where does it go? Metals lose, non-metals gain, right? So reduction is the gain of electrons, right? So an element or compound that gains electron or electrons is said to be reduced. So they're kind of a pair, hence redox is kind of an acronym. Okay, now there's a couple of ways you can remember this. If you've taken a biology class and they talk about electron chains, because redox reactions in ATP and things like that in the body are very, very important. And you may have seen this if you've taken a biology class. Leo says grr, right? Loss of electrons, oxidation, gain of electrons, reduction. That's one way to think about it. If you learned that one, fantastic. But, you know, I prefer a more kind of macho chemistry kind of way to remember, okay? So get this image in your head, right? So get this image in your head of an oil rig, right? So there's an oil rig. And the oil rig is staffed by friendly electrons, right? So there are some electrons working for BP or something, right? So there they are, right? So I always like to think of oil rig of electrons, right? Oil rig of electrons. Oxidation is loss, reduction is gain of electrons. Oxidation is loss, reduction is gain. So if you remember oil rig or Leo says grr, either one's fine. The trick with this, well, the trick with electrochemistry in general is just keeping the definition straight. If you always remember oxidation is loss of electrons and reduction is gain of electrons, you don't get the two processes mixed up because it's very, very easy to mix up the two processes. Okay, so always have that in your mind. Okay, so moving forward, here's a very, very simple redox process, one we've all seen before. Okay, so whenever I make a salt, an ionic compound, I think about an atom of sodium bumping into an atom of chlorine. Well, what happens? That electron jumps across due to a difference in electronegativity. Sodium obviously low, chlorine high. And what do we make? We make an Na plus ion and a Cl minus ion. Those ions then, of course, stick together because of electrostatic attraction. Okay, plus attracts minus. Okay, so how do we kind of represent that in kind of a formal way using redox, right? So ask yourself a question, who lost and who gained, right? So oxidation is loss. I write it over here, oxidation. And reduction. So there's always what we call two half equations, right? Oxidation is loss of electron. Reduction is gain, right? When you look up here, well, who lost the electron? It was sodium, right? So sodium was oxidized. Metals become oxidized. Rusting is oxidation, right? So if you'd like to think about rusting, that's a form of oxidation. Metals rust, right? So oxidation is loss. There's kind of what we call a half equation. So it's just thinking about the one of the two steps. Oxidation step and then reduction step, well, chlorine accepted that electron, right? There we go. Nice and easy. So those are our two half equations, we call them. Okay, the oxidation and reduction half equation. And together they, you know, we see the generation and the acceptance, if you like, of an electron. So you have to have the same number of electrons consistently between the two half equations for this to work, and it's kind of easy here, but later on when we do balancing redox, we'll make sure that happens. Okay, now you can of course take those two half equations, just like we've done many times in Hess's law and things like that. Just combine the equations to get the final net equation. So, you know, take those, combine them. So Na plus an electron plus a Cl goes to Na plus an electron plus Cl minus. What cancels? The electron. And in any redox process, a consistent number of electrons must cancel. That implies correctly balanced. Okay, I can't transfer a different number of electrons. What's lost by one is gained by the other. It has to be the same number. Okay, so the final equation is just gained by combining the two half equations. All right, so hopefully that's kind of familiar. Now, how we kind of treat redox is with what we call oxidation states or oxidation numbers. There's a very subtle difference between an oxidation state and an oxidation number, and to be honest, it's oftentimes the same thing. Okay, sorry, I should say charge on an ion in oxidation state or oxidation number. Often it's the same thing, but when we talk about molecules, it's subtly different. Okay, so what is the oxidation number or oxidation state? Well, it's the charge on an atom as if it were an ion. Okay, so Na in the previous example, Na is a +1 here. We say it's got a +1 oxidation state. Okay, so we say oxidation states with a Roman numeral +1 oxidation state, but it's a charge of +1. So it's kind of a subtle difference. Really, oxidation states are used for accounting. It's kind of an accounting mechanism. Okay, so I can work out kind of oxidation states for weird things that aren't ions later, but for ions it's actually the same thing. So for now it's easy, but later on it will be different. And remember, oxidation state is kind of a Roman numeral there. Okay, so for simple atomic ions, it's the same. Okay, so for sodium in NaCl, right, when we've got Na plus in there, right, that's just a +1 oxidation state. In the book, they generally drop the plus. I like to kind of include it because, you know, there are plus and minus versions. All right, so think about, you know, group 1 makes +1, nice and easy. Magnesium's group 2, so +2 minus 1 need 2 of them, right? So that's obviously a +2. All right. Try the others. Okay, try the others. This one here in particular, when I teach, you know, ionic compounds and their formulas in Chemistry 100, this is kind of the capstone question, right, for Chemistry 100 students. Can they tell me what the charge on this iron is, right? Okay, so it's kind of the same question for you guys, all right? No stress, okay? So, you know, obviously use periodic table as a guide, group 1 +1, group 2 +2, group 7 -1, group 6 -2, we know that for sure, right? But iron, because it's transition, we'll have to work it out. Okay. All right, let's take a look. So aluminum's a +3, chloride is -1, and there's 3 of them. So chloride in aluminum chloride is actually -1, all right, -1. Then iron in iron oxide, this is rust, right? So iron can be +2 or +3. So is that iron +2 or iron +3? That's the question. Well, it all adds up to 0 if you remember your general chemistry, you know, 101 or 100. So 3 2s are 6, so together this is 6, so 2 3s are 6, so that's iron +3. So rust is actually iron 3 oxide. That's what rust is. Okay, it's iron 3 oxide. Okay, so hopefully that's a nice reminder. Keep going. Now, for any element, if you think about it, I'll just do it on the side real quick. For any element, the oxidation state must be 0, because if you think about an element, the electrons are right in the middle for that covalent bond, right? Even if it's a metal, right? So we have a metallic bond or a non-metal's covalent bond, right? So if it's an element, they have identical electronegativity, so they pull with identical strength, those electrons must be right in the symmetric middle there, okay? So no one loses, no one gains. It's not like Na goes plus and Cl goes minus. It's, hey, no one wins, no one loses. If no one gains an electron, no one goes minus. If no one loses, no one goes plus. No plus, no minus created. We say it has a 0 oxidation state. So by definition, all elements have a 0 oxidation state because they're, if you like, haven't gained or haven't lost electrons. That's a nice way to think about it, okay? So it works for diatomic or other molecular elements, O2, F2, even O3 or S6, things like that, okay? And metallic elements too, okay, like silver, lead, gold, whatever you like, right? So anything that's just the atom stuck to its own kind, if you wish, is always a 0 oxidation state, Okay, so simple ionic compounds, it's their regular atomic charge. Elements, it's 0. But what about oxidation states inside molecules? And this is where it gets a bit funky, because molecules, if you remember, aren't made from ions, right? So we can use the accounting trick with oxidation states to figure out some neat stuff. But remember, there's really no such thing as an N+5 ion, right? And, you know, we may find, for example, the oxidation state of nitrogen in a compound is +5, but that's just an accounting thing. It's not really a +5 ion, is it? Okay, so let's take a look at this kind of sum of the oxidation states rule. Okay, this is how we work out the individual oxidation states inside here. Now, the big trick, if you remember the trend in electronegativity, this is one of my favorite kind of slides. I can't remember where it is now, but hey, fluorine is the king, right? Fluorine has the highest electronegativity and cesium has the lowest, and that's the trend in electronegativity, low to high, right? So always kind of keep that in mind when you have a question like this, because we have hydrogen, which is going to be kind of the weakest, if you wish. Okay, it's going to be more to the left. Then we're going to have oxygen. If we look in here, it's nitrogen and then oxygen, right? So oxygen is going to be more to the right, so it's going to be the stronger of these two. And that leaves nitrogen, if you like, as the sandwich. Sorry, the meat in the sandwich, right? So this is going to be a loser, this is going to be a winner in terms of electronegativity. This is going to be the one that changes to accommodate for their normal oxidation states, okay? So things that are the weakest and the strongest will acquire their normal oxidation states, the charge they would be in an atomic ion. So that's going to go +1, that's going to go -2, and there's 3 of them. That will change because the molecule itself has no charge, okay? So for molecules, the sum of the oxidation states with the one in the middle, a variable, adds up to 0. A nice way to think about it is to do like a little table. I mean, you can probably get used to this pretty quick. And honestly, later on, we'll just be writing in these numbers. But here's a way to think about it. So there's my sum of the oxidation states is 0, right? So 0 means sum of oxidation states, because it's a molecule, it's going to be 0, right? Now hydrogen, there's 1 of them, and it's a +1 oxidation state, so its contribution is +1, if you like, all right? Oxygen, the other piece of bread in the sandwich, so that's the weakest, that's the strongest. This is going to be its natural oxidation state. Now in here there's 3 of them, and it makes a -2 oxidation state, which has a contribution of -6. Now nitrogen, there's 1 of them times the mystery oxidation state equals X. If there were 2 nitrogens, it would be 2X, right? And we're solve for X. But hey, we've got to solve for X. So -6 + 1 plus something is 0. Obviously X is, you guessed it, 5, right? But +5, now we say oxidation state +5. There's no such thing as a +5 nitrogen ion, no such thing, particularly in this molecule, right? But for accounting purposes, and when we do redox, we need to keep track of where electrons are going, and this helps us do that. So we say it has an oxidation state of +5, okay? Now, so we'd write nitrogen, if this was the test, +5. All right. So there we are. Now, little trick, if you look in the periodic table, nitrogen is in, classically, obviously, column 5. It has, if I did its Lewis real quick, and I can do this down here, 1, 2, 3, 4, 5. It has 5 valence electrons. Oxidation state 5 often is the same as the group number 5, because it's really counting how many electrons are being utilized in bonding. That's what's going on. So inside the molecule, all 5 electrons are actually being used. If you did the Lewis structure for nitrate, you'd see those electrons and where they were. Okay, but oftentimes, cut to the bottom line here, oftentimes the oxidation state is the same as the group number because it's counting the number of electrons utilized in bonding. All right, so got a bunch of practice questions. All right, we'll try those in a little bit. But first, let's look at a few more kind of subtleties with this model, right? So polyatomic ions, otherwise molecular ions, right? So charged molecules. In this case, the sum of the oxidation states equals the net charge. So here it's going to add up to -1, right? To -1 because it's a -1 ion. Same as before, feel free to pause and try it, but I'm going to do the same thing I did before, but it's going to add up to -1, right? So who's the winner? Well, hydrogen's not there. Oxygen still is the winner in terms of the strength of electronegativity. So there's 3 times -2 equals -6. Nitrogen, there's one of them, times its magic number of oxidation state. So what combined with -6 is -1? Well, obviously it's 5 again, right? So again, nitrogen's a +5 oxidation state. Maybe that shouldn't come as a surprise. Nitrate is just, you know, nitric acid with the H plus falling off, so it's the same really. Okay, so that's how you work out oxidation state of kind of, if you like, sandwiched atoms inside molecules and molecular ions. Now, there's always a few weird exceptions, okay, always a few weird exceptions, okay. Now, those exceptions would be, for example, if something is bound to itself, so oxygen bound to oxygen when inside a molecule, right? And that does happen occasionally, and we'll look at dihydrogen dioxide or hydrogen peroxide in a moment. Or what happens when we have fluorine? So obviously fluorine is always the winner, even if it's with oxygen, and we get a little bit confused sometimes because we all think, oh, oxygen wins. Well, it does win all the time, except when bonded to itself or when bonded to fluorine, okay? So let's just kind of answer the question. Oxygen is always a -2, except when bonded to another fluorine of itself. Why? Because when it bonds to itself, no one wins that tug of war, okay? So no one wins or loses if two oxygens are stuck together, all right? And if it battles fluorine, fluorine always wins, all right? Because fluorine has a stronger electronegativity. Now, when we do these questions, obviously they're going to give us kind of unusual answers. And the best way to think about it, if you go back to your Lewis structures, is to draw one. Okay, so this is the only way two oxygens and two hydrogens will stick together, to have the, you know, one bond to hydrogen, two bonds to oxygen. And you know, if you want to put the lone pairs in, you can. That's a bit type A, but there you go, right? All right. Now, think about this from a common sense point of view. In the tug of war between oxygen and hydrogen, who wins? Well, oxygen. So oxygen goes -1, this goes +1 in terms of an oxidation state. Same kind of deal up here, -1, +1. And then I want to look at the tug of war between these two. Who wins? Well, neither, because they're the same atom. Normally one would take an electron and go -2, right? As normal as for oxygen. But no, that's as far as it goes, right? So it's kind of a weird answer. Hydrogen is normal, oxygen as the variable. So we can do a little map there, right? So hydrogen, oxygen, and it all adds up to 0. We remember the unique weird thing is this bond here. So I'm going to make oxygen the variable and hydrogen the fixed. So 2 times 1 is +2. Oxygen, there's 2 of them, times the magic oxidation state is 2x, right? So we want to find the oxidation state of 1, but there's 2 of them, so it's 2x. So a +2 combined with 2x equals 0. Obviously x equals -1. Therefore, oxygen is a -1 oxidation state in hydrogen peroxide. Very nice. Hopefully that makes sense. All right. Talking about this guy here, if we do OF2, we do a quick Lewis. There it is. I won't draw the superfluous electrons, right? Okay, so there it is. Okay, now who wins, you know, if we just do common sense, who wins this tug of war? Well, that goes -1, that goes +1. Oh, that's weird. Oxygen's a +1. No such thing as a +1 oxygen, right? But oxidation state's +1. -1, +1 again. Oh, 2 + 1s is a +2. So we're going to predict a +2 oxidation state for oxygen. Fluorine, it's regular, right? So fluorine always wins, doesn't matter who it's with except itself. Oxygen's the variable. So fluorine, 2 times -1, -2. Oxygen, 1 times x equals x. It all adds up to 0. It's a molecule. X equals +2, right? So fluorine is -1. Oxygen's +2. Oxygen +2 oxidation state. Again, no such thing as a +2 oxygen ion. In this molecule, for accounting purposes, it has an oxidation state of +2. All right. Now remember the golden rule with the electronegativities. Further to the top right you are. So fluorine will always beat everything except itself. Oxygen beats everything except itself and fluorine. And then we go down the line. Chlorine is the next strongest, bromine, then iodine. Okay. All right. Examples. Now, these, plenty of examples, right? So I'll do 2 more, and then I really advise you to pause and kind of try these guys down here, all right? So if you feel confident, pause right now. But if you need 2 more examples, I'll go through them. And then, you know, try these. Okay, so ClO2 is an it's a molecule with no charge. All right, so it all adds up to 0. The winner is oxygen. chlorine loses to oxygen. So oxygen is going to be 2 of them, times minus 2 is minus 4. Chlorine, 1 times X equals X. X and minus 4 is 0. Chlorine is a plus 4 oxidation state. Where does that sound? Chlorine in ClO2 is a plus 4 oxidation state. You may be getting to the point where you can just look at it and figure it out, right? You just say to yourself, well, oxygen's the winner, so it's going to be, 2 times minus 2 is minus 4, so chlorine must be plus 4. So you can kind of do this math on the fly if you wish. It's kind of harder to do math on the fly for ions, but we'll do the grid then, or the table rather. So chlorine, oxygen, adds up to minus 1. Oxygen's the winner. 3 times minus 2 is minus 6. Chlorine, 1 times X equals X. Something with minus 6 makes minus 1. Obviously, oxygen is a plus 5 oxidation state. All right. A little different than the previous one. I recommend for ions always to kind of do the little math on the side. All right. So give the remainders a go. Hopefully, you can just look at it and figure out the answer. All right. So here, sulfur is going to lose to oxygen. Oxygen is 3 and it's a minus 2, so the oxygen component, if you like, and you can start doing this down here, right? So this is 3 times minus 2 is minus 6. That needs to be a plus 6. Where's sulfur in the periodic table? Column 6. So all 6 electrons are being used for bonding. All right. If you did if you remember Chemistry 101, you do an expanded octet for that and you'd see those electrons. All right. Xenon, if you did the Lewis XeF6, xenon hexafluoride, there it is, okay. So xenon is actually the variable here. Let's do it anyway. Xenon, fluorine, you can probably see where this is going. Adds up to 0. Fluorine is minus 1 times 6 is minus 6. Xenon is 1 times X. It must be plus 6. So xenon in this compound is a plus 6 oxidation state. Obviously no such thing as a plus 6 xenon ion, right? But in this compound it's a plus 6 oxidation state. Sulfur and sulfate ion, obviously we're going to do the math for this one. So sulfur, oxygen. Sulfur loses, oxygen wins. 2 times 4 minus 2 times 4, 4 of them times minus 2 is minus, switch those, but hey, you got it. Here 1 times X equals X, it must be 6. Sulfur, 5, 6 again. Oftentimes sulfur is a plus 6. Chromium. Chromium is the highest oxidation state of any compound in this chromate ion. Okay, so let's see what the highest possible oxidation state is. Okay, all right, so it turns out chromium, oxygen wins. Adds up to minus 1. Oxygen, 4 times minus 2 is minus 8. Chromium, 1 times X equals X. X must be, you got it, 5, 6, 7. So plus 7 oxidation state. That's why chromate is an excellent, what we call oxidizing agent, because it has the highest oxidation state. It wants to get lower. I would say that when we talk about redox equations. All right. Finally, last row here. Careful. If you think about this too quickly, you get the wrong answer, right? If you think about electronegativity between sodium and hydrogen, well, you say, oh, hydrogen always is the loser. No, not in this case, okay? Because hydrogen is actually, bottom left is the lowest, top right is the highest electronegativity. So hydrogen is actually more electronegative than sodium, okay? So hydrogen is going to go minus, sodium is going to go plus. So sodium will get its plus 1 charge. Hydrogen, what's it got to do? It's going to go minus 1. So we're going to get H minus 1. And that's called the hydride ion. Interesting and important fact that, because when I mix hydrogen with nonmetals, HCl for example, it makes a plus sign, makes the proton essentially, right? It's for acids. But when I mix it with metals, it goes minus, because it sits right on the border between metals and nonmetals. It can go either way. With a metal, it goes minus, makes a hydride ion. Lithium hydride, for example, is used a lot in batteries. Okay, but when it's with a non-metal, it's plus. So the kind of dual personality of hydrogen there. All right, finally, you can work this out, but hopefully you're having a flashback to Chem 101. Magnesium makes a plus 2 ion, nitride makes a minus 3, but let's just confirm it. Let's just make magnesium the fixed plus 2. So there's 3 times plus 2 equals plus 6. Nitride is 2 times x equals 2x. It adds up to 0. Something. So 2x equals minus 6, x equals minus 3. Yeah, no kidding. Nitride is a minus 3 ion. Yeah, we know that. It's a minus 3 oxidation state. All right. So, making good progress there. Okay, now give that a little practice, because the next thing we're going to do, we're going to come back, in the next video, and we'll see how we use these oxidation states to actually balance redox equations. Now, the redox equation is quite a process, okay? It's a multi-step process, and we'll go through that in the next video in more detail. Okay, let's stop there.